Hey all you guys, gals, and physics pals, welcome to Quantum High, modern physics for high schoolers. Now let's get talking. Now, most likely in your class you've heard about two different things, the theory of relativity and quantum mechanics. Now, what's the key difference here? Now let's start with the theory of relativity. Einstein devised this when he was 26 and published his paper with two main theorems. One, that light speed was constant throughout the universe, and two, that the laws of physics held in any inertial reference frames. Now, what exactly does that mean? So a reference frame is any specific point an observer within an environment. Now, regarding different reference frames, Einstein realized that to keep the laws of physics intact and the Maxwell equations, he had to find that the simultaneity of different events in reference frames was not correct, which resulted in Lorentz transformations, which results in time dilation, length contraction, which I'll talk about in another video. Now let's get into talking about the constancy of light speed. Now this was a very strange aspect because it meant that Newtonian physics was incorrect at very, very high speeds. And so Einstein realized that the Maxwell equations couldn't be satisfied at high speeds, though if Newtonian physics was held correct. So Einstein never actually proved this, he just speculated this. What really proved this was something called the Michelson-Morley experiment. Now, in this experiment, they decided that if there was an absolute reference frame, that there would have to be an ether, some sort of undetectable substance out in space that would allow light to propagate through. They designed an experiment where they had a rotating wheel, and on that wheel they'd shoot a beam, it would reflect back, and the difference in the reflecting beam going through the mirror and apart from the mirror would give a difference in time. And if there was a difference in time, it would prove that the speed of light was constant, and if there wasn't, then it would prove that there was an absolute reference frame. Now, after a lot of math, Michelson and Morley just figured out that the speed of light was constant and that there was no ether or universal reference frame. And that really set up Einstein and his theory of relativity, as well as the denial of the spontaneity of events in different inertial reference frames. Now, through all this being said, all this throwing out of Newton's laws and observation of Maxwell equations, that's not to say that Newton's laws aren't correct at really low speeds. They are. They're very, very near approximations. But it only is affected at very, very high speeds when velocity is approaching c. That's when you need to use the Lorentz equation, Lorentz transformations, to adjust for the theory of relativity. Now let's get into some quantum mechanics. And quantum mechanics was designed to describe movements of subatomic particles, like electrons, etc. And the key aspect of quantum mechanics is that subatomic particles can be treated as waves. Matter can be treated as waves, like kaboom. That's just absolutely crazy to think about, because you think, oh, particle hits. It's a particle, you look at it, you see where it is. But one key aspect of quantum mechanics is that particles exist as waves. Now, that comes from the de Broglie, I don't know exactly how to pronounce his name, experiment, and his thought processes about how if what Einstein said about photons being able to be treated as matter, why can't matter be treated as waves? And that really struck the world, thought it was an absolutely crazy aspect, but he went in to prove this theory. Now, what de Broglie wanted to do was to prove that if wavelength equals h over p, or momentum, for photons, then why couldn't it be the same for electrons? And so he took this and did a lot of math, which I'm not going into, and found out that, in fact, yes, it does equal that. And how he based it on was because of Bohr, and what Bohr did with the quantization of energy within the hydrogen atom. And now Bohr had asserted that there had to be a quantization of energy to allow for the emissions in photoelectron spectroscopy, and allowing that photon to emit a certain amount of energy, E equals NHF. This quantization of energy had been proven by Hertz and Frank experiments, and it's showing that as energy went up, it did this, and then it cut down and jumped back up and every cutback happened at a specific E equals NHF. All of this said, this resulted in having to define particle motion as a wave function, which we'll get into when I talk about the Schrödinger equation, which is just that, a wave function describing the movement of particles as they go along. Now, with all of that crazy information being said, I want to just make sure we review all this and then talk about the conflicts between the two. The theory of relativity is much more realistic at a very, very large scale at high speeds, and quantum mechanics is much better at describing the world at very, very small subatomic areas. Not to be said that either one is true or not, they're both theories. That's all for the video. Hope you learned something. And I give you a quantum bye. Get it? Now, I hope I didn't leave too many open spaces. This is my first video, so I don't know entirely what I'm doing, but hopefully I answer most of those open spaces in future videos regarding Lorentz equations, time dilation and length contraction, and the Schrödinger wave equation.